I'm Glauber Costa, and I'm a principal architect at ScyllaDB. Now, this role that I have in this company is an interesting one. I get to spend around 70% of my time doing engineering, developing some of the new features that Scylla will have in the future, that Scylla has in the present. And the remaining 80% of my time, I get to spend with our customers, open source users, current and future. And as some people remarked that I met today in the morning, yes, I am a real person. I'm not just a Slack bot. So, as Alex said, today I'm going to talk to you about latencies, which is something that I see in the field that is dear to most of our deployments, to most of our customers. And the interesting thing about latencies is that when we talk about latencies, it's not enough to talk about averages. We need to look into the entire distribution, especially the higher percentiles. Now, distributions have many names. Does anybody here knows the name of a distribution for which the higher percentiles are much higher than the average? Garbage collector? No, that's not the name of the distribution. But we can go with that, yeah. What? Failure. Well, there are many names. I mean, there's not like, unlike the normal distribution, there are many names for that we can use. Data set. I'm not here to bash anybody. But in Scylla, we have a special name for such distributions. We call it a bug, right? And obviously, how high is too high is up for the workload to determine. One obvious example of that is a workload, like if you have a read workload, some requests are coming from cache, some requests are coming from disk. Obviously, the higher percentiles are going to be higher, they're expected to be higher. But what we see in practice, like with other databases, is that the database tends to make it worse than the actual just speed of the disk. And in Scylla, if it do happen to make that worse, we consider it a bug. And as you will see, I mean, it makes all the difference in the world to view high latencies as a bug that we can fix and not as a fact of life under any circumstance. And that is part of our autonomous operation promise. You should be seeing consistent latencies, right? If your latencies go up, they should go up equally, all the way, not just in the higher percentiles. To understand how to view those problems and how we fix most of them, we need to understand first and foremost, where are those latencies coming from? And I'll talk about three sources of latencies. The first one being speed mismatch. We have speed mismatch when we have two entities or more, and one of them is much slower than the other, like the cartoon. The slow one will try to chase the fast one, but it usually can't. It can try all the shenanigans in the world, it can't really do that. And in real database systems, the fast one tends to be the CPU, or not a single CPU, but like all of them. And the slower one tends to be the disk, even though this equation is changing a little bit. We're going to see presentations from Intel and Samsung with incredible disk technologies that they have. But in most deployments, CPU is the fast one, the disk is the slow one. And when you have a write workload, so for this one particular, I'll focus in write workloads. When you have a write workload, we know that Scylla, like other NoSQL databases, we acknowledge requests when they are in memory, way before they're written to disk. But those requests have to be written to disk at some point. So your writes are fast at first, but if you keep writing, and that's one of the issues that Naiden talked about in this presentation, if your workload keeps pushing and pushing and pushing, when time comes for you to actually write that to disk, you're going to have a problem. You are forced to stop serving requests. If you don't do that voluntarily, your node is going to crash because the memory to hold that is a finite resource, and you're out of luck. And let's look here. If we see the kind of latencies that we're talking about, you can see this problem. So the mean is not bad. I mean, the median is fairly low, but the 99 percentile and the 99.9, they're over a second. We call this problem the wall. And the reason we picked this name is that the behavior of the system is as if I'm running really fast, now my requests are coming as fast as memory and CPU allow them to, and then they hit a brick wall, and they had to stop. And again, that is not a choice, because one thing is faster than the other. What we would like to do is spread those around the entire distribution, so you don't see higher percentile latencies that are too high. And how we fix this, how we fix the wall, we were able to fix it by leveraging our architecture and the proximity it has to the hardware. Now you see, when Scylla writes to files, we're not writing to buffers. We don't use the Linux page cache. We don't use any other form of operating system buffering. And what that means is that we always know the exact speed at which the disk is able to flush things, even if you have other stuff going on with the disk. And that is the speed our pointer inside that buffer advances. And once we realize that, through leveraging our architecture, we are able to very easily fix this problem. Now, we only allow this buffer to grow over a certain limit, and when it reaches that limit, we stop requests, but not for a long time, just for time enough so that the size of that request worth of memory is written to disk. So for every byte that we write to disk, we allow a new byte to enter the memory buffers. And just like that, we fix this problem. And you can see here in the graph how that works in practice. The system starts really fast, right? But once I hit this buffer limit, and that is the important thing, and that, again, that's our promise of autonomous operation. Without any human intervention, through an algorithm, we reduce your request rate to disk speed, right? And if you look at the latencies, the median is now a lot worse, but that is a good thing, because the 99 and the 99.9, instead of 22 times higher than your average, are now only 4.6 times higher than your average. What we did is we spread those latencies that, again, we have to introduce. It's not a choice throughout the entire distribution. Where is this problem with the wall relevant? Mostly with write workloads. That's not a read problem. There's a write problem that are bounded by the disk. So workloads, write workloads, that are disk bound. It can happen just because the disk is slow, or it can happen because your payloads are too big, and your payload being too big usually shifts the bottleneck to the disk. Where else is the wall relevant? Well, in the north, it keeps us from ice giants and stuff, and as I have been told, in the American elections. The second source of, I'm not going to expand on that, but the second source of latencies is lack of respect for limits. I see that the folks with small kids in the audience have this nice smile on your face. But before I tell you what this problem is, and again, what we did to fix it, I need to tell you about how Scylla processes its internal tasks. Traditional systems are usually multi-threaded, and you have all those threads fighting for control of the CPU. Scylla employs a totally different architecture. We are a thread per core system, and that means that every CPU has a single thread running, and inside that single thread, we have a scheduler that is scheduling those small continuations, as we call them, which are usually fairly small and fast tasks that do some I/O, and one example of that would be I'm doing some network request to a replica, and then I wait for this request to come back. When it's back, I'm back to the back of the queue, and that's basically how it works. If we dig deeper into that, you see that the tasks are arriving, so they are like the gray things in there, right? That's a task. And I execute 1, 2, 3, however many I need. But every once in a while, I need to stop executing those tasks, and I need to run something we call the pollers. They basically go check if there's any I/O that is available, there's any I/O that completed. And most of the tasks, as I said, are fairly small, fairly efficient, but some of them are not. They could be, for example, calculating a hash or doing any kind of CPU-intensive computation that may take more than we would like them to do. This blue thing here, the pollers, they happen periodically, and that period we refer to as the poll period or the task quota. Now, the more often we poll, the better your latencies are going to be. But your throughput tends to decrease because that's a fairly expensive process, and you trade one from the other. Prior to 2.0, our polling period was larger than a millisecond, which made it hard for us to uphold latencies that were smaller than a millisecond. Basically, you're not going to get I/O before that. In 1.7, we've done a lot of work to improve the speed and scalability of the pollers so that we can do this more often and provide you with better latencies. And in 2.0, we reduced that period fourfold. So now we are way under a millisecond, and we are in a great capacity, in a great place to provide you with sub-millisecond latencies. Further to that, we have merged something that's called the block detector. What the block detector does is that it will try to detect those guys here that are holding the CPU all together. And there's probably nothing we can do about that because it is computation that it needs to be done, but we can probably preempt this guy so that he doesn't affect latencies for other things, right? And this block detector will warn us about violations of the task quota, meaning something run for more than the poll period and we couldn't do I/O when we wanted to. We'll print a message about that with information about that occurrence to the logs, and hopefully, by knowing about them, we'll fix them one by one. In the 2.0 release, our QA has extensively run every test they possibly could with the block detector enabled with very low thresholds. We are now aware of a host of occurrences of which, like tasks were blocking the CPU, and we fixed a lot of them. Some of them were postponed, and in future releases, like right now we know there are some that still need fixing. In future releases, the idea is that every system running Scylla will have a block detector enabled with low thresholds. So if any task runs for more than, say, like maybe 1 millisecond even, we will be notified about that fact so we can fix it. As I said, that really shows that those things for us are bugs. And we are committed to fixing them one by one until they're gone. All right. Now, the third source of latencies for some of the AMC fans out there is imperfect isolation. Right? From its very beginning, one of our defining features, one of the things that is with us in Scylla for a long time, pretty much before our GA even, is the I/O scheduler. When you install Scylla, we will run a small benchmark that will try to determine what is the sweet spot in terms of disk concurrency, in terms of concurrency that your disk can do. SSDs, like modern SSDs, modern storage, they are incredibly parallel. You add more requests in parallel, your throughput tends to increase, but that only goes so far. At some point, you saturate the device, and you can send them those requests all right, but they're going to be queued inside the disk. There is no point in doing this. And again, our architecture, our close-to-hardware architecture, allows us to do something different. We have an I/O scheduler inside the database, and that I/O scheduler, the first thing it does, it will guarantee that it will never send to disk more requests than your disk can handle. And by doing this, we can queue those requests inside the database, not in disk. And what that allows us to do once they're queued is to tag them. You can see like examples of classes that get a tag: query request, compaction requests, commit log writes, so on and so forth. So even if you have a compaction that is running and using the disk to its fullest capacity, to 100%, a lot of queue requests, when a query request comes in, we are able to serve it with low latency because the compaction requests are still queued inside the database. But that's in the past. I mean, that's already something that we do very well, and we need to look further. The I/O scheduler works really well. It's one of the pieces of technology that we have in Scylla that really helps us deliver our promises. You've seen, by the way, an example of that in Aiden's presentation, where we had all the compactions running. They're running compactions extremely aggressively, but the load doesn't budge. We managed to keep the latencies even in the face of compactions. It's not perfect, and we are very perfectionists in this company. We would like it to be perfect, and some of the problems we are aware of is when you have a very big distribution of request sizes. So we know we can do better, and we were working on that. But by and large, the I/O scheduler works really well. And indirectly, it even allows us to control your CPU usage rate. The way we do this is most of our processes, most things that happens inside Scylla, like compactions, like repairs, they have limited parallelism. So when the disk becomes a bottleneck and the requests are sitting in the queue because something else is running, those things, those entities, compaction, repair, they're not going to send more requests down the disk. And just like that, through I/O, we also control the CPU. Now comes those extremely fast disks. We're going to have talks today, as I've already mentioned, from Samsung, from Intel. We have Amazon i3s that we're having the demo booth outside. The Amazon i3s, for instance, the machines are 16x large. They can do 10 gigabytes a second worth of I/O with more than 1 million IOPS. So in systems like that, the bottleneck changes. And most of the time, you can still bottleneck the disk, but most of the time, we're going to start being bottlenecked by the CPU. And what we would like to do is implement something like the I/O scheduler for CPUs. Because the scheduler that lives inside that event loop that I showed earlier, it is really simple. It just queues stuff in a first in, first out queue in the hopes that the system, as most databases are, will eventually become disk bottleneck. 2.0 ships already with a CPU scheduler. It is an initial version, not complete. We're hoping to have the complete thing in 2.1. The 2.0 version is able to isolate at the CPU level compactions and memory flushes from the foreground requests. So if you have a compaction that is now not bottlenecked by the disk, before 2.0, you would see that maybe dominating the CPU. In 2.0, they're bounded as well. And the scheduler will guarantee KOS in that thing as well. 2.1 will just isolate better. We're going to have the full version of the scheduler. And we'll also be able to isolate more things. Right now, we are only doing compactions and memory flushes. We want to isolate repairs and any kind of message that you think that might be important to isolate, we'll isolate that. And on top of the CPU scheduler, we're implementing something called the controllers. And I brought you an example so you understand what the controllers are and again, how that ties together into the autonomous operation promise that we at Scylla make. This is again a write workload, and we are trying to write at a fixed throughput here. That doesn't matter the number, but we're just trying to go. And we do, until we need to flush that memory to disk. And those disks that I'm having here in this benchmark, they are incredibly fast, like much, much faster than the CPU. Now you see, the throughput doesn't suffer when we flush, because whichever requests I didn't execute here, I'm queuing, and I will execute later. That's the spike that you see here. But the latency in that, during this period here, it's not great. And you see how fast we're actually managed to flush, because the disk is extremely fast. But what happened in this time here? In this time, we're not flushing, so flush is basically a spike. What that means is that we can force this flush to be slower. So most of the time in Scylla, we're talking about things that are going faster and faster and faster. With the controllers, we want to find background processes and say, you should go slower, so you don't mess with the requests, with the foreground requests. And even if the CPU scheduler is enabled, right, it will guarantee some level of isolation, but those flushes can still go pretty fast. We don't want that to happen. The controllers draw from the mathematical and theoretical foundation of industrial controllers. Things like the PID controllers and other controllers that we found in the literature that we brought into ScyllaDB. It's not very different than controlling, for instance, It's not very different than controlling the level of a water tank. For every entity that needs controlling inside Scylla, we allow that entity to define a backlog. A backlog is a measurement of how much work that entity has left to do. One example, so everybody understands, in the case of memory flushes from memory to disk, the backlog is basically the amount of memory that we have that is not yet written to disk. As we write one request to disk, and again, we can have that at request granularity, at byte granularity, the backlog decreases. And every new request that comes into memory, the backlog may or may not increase. I mean, if it's an update, use the same amount of memory. And again, the beautiful thing about that is that it's all automatic, no human intervention whatsoever. Let's see how that works in practice. So we have the same example that we ran before, but now I'm running it with the full power of the controllers. And as you can see here, the controller determines the level at which we would like that backlog to be. And it will give more or less CPU to that process, to that entity, so that the backlog is at the level that we want it to be. If we are flushing too fast, the backlog drops too fast, and we say, hold on, you're going to use less CPU now, buddy. If it's creating a backlog, okay, you need to go faster, otherwise we're going to run out of memory, and I'm going to give you more CPU. So this is a constant write workload. And as you can see here, the quota or ratio, it's actually a ratio of CPU that the controller determined is pretty much stable. So it's a stable ratio, so that the backlog is at the level we want it to be. So the backlog is now stable, and the CPU rate is stable. And as a result, the throughput barely oscillates. And of course, those periods of drops, they will increase latency in that period. We don't want that. The CPU load is also extremely stable. And it is at 100%. You're paying for the CPUs after all. But the CPU controller is able to guarantee that those requests, those flushes, will never use more CPU than we allow them to use. So yeah, you're 100%, but I can guarantee you that you're not going to use more than a certain level, in this case, 50%. Look at the difference. Before and after. And if we look at the actual numbers, right? The latency, the mean, the median, etc., they don't change much. But the 99th percentile, look at that. From 6 times higher than the mean goes to 2 times higher than the mean. So we fixed that bug through our architecture, through interesting technologies like the controllers. Things that automatically determine the rate at which entities and processes inside Scylla have to operate. Not you. You will get it wrong. Everybody gets it wrong. But those algorithms, I mean, they're proven, they work, and they automatically do that for you, autonomously. Flushes are already a solved problem in 2.0. They're already there. We don't enable them anywhere. They're an experimental feature. But we enable them by default, for instance, in the i3 classes of machines. And you can always test it. You can always use them. I personally do consider them production ready. In 2.1 and in future versions, what we want is we want more entities, not just flushes, to be controlled as well. In particular, compactions. We want compactions to be CPU controlled, automatically determined, so your compactions will never go too fast, and they will never, as well, go too slow. If they go too slow, I mean, we create backlogs. We have seen, again, in earlier presentations, how detrimental that is. We also have the same thing. We have controllers as well for things like repairs. Soon, we're going to see, we're going to have some talks about our enterprise repair scripts. And we are already able, in Scylla, to run repair with minimum disruption to the foreground workload. But because repair is a CPU-intensive process, we need to do it by artificially limiting a little bit the speed at which repairs can go. With the controllers, we're not going to need to worry about that. And we're going to be able to unleash the full potential that repairs have. So they're much, much faster than they are today. We are already faster than the competition, but we want them to be as fast as they can possibly be. Summary of today's talk. At Scylla, we believe that high percentile latencies should be low and should be bounded. We do not believe this is a nice to have, and failure to do so is considered by us to be a bug. So far, especially in the past year, we have fixed a lot of those bugs. And while there is a lot more to fix, software always have a lot more bugs to fix, right now, today, Scylla users are already in a great position to take advantage of that automatically in a wide variety of workloads. Thank you. If you have any questions, I have 5 minutes. There's a question over there. We need a mic to get. The question is there somewhere in the middle of the light.
Hey, can you hear me?
I can hear you. Yeah.
Can you talk a little more about how the CPU scheduler is going to be integrated into the futures? Are you going to be returning a different type of future, or how the controllers work? And or is it going to be controlled in the same way that I/O is controlled with basically a set of priorities for, so right now you throttle your disk I/O because you give it a set of priorities,
Yep.
which converts to 2 shares of the I/O scheduler. So can you give more details about how that's going to work?
I sure can. So the future types doesn't change. And just so we clarify, I know you are a Systar user and developer as well. So the CPU scheduler, it's in Systar, and it's actually already merged. You can look it up. The futures don't change. What you change is that you can specify a scheduling group at which you believe this group of tasks should belong. So in your application, you could say, okay, that belongs to this scheduling group, that other belongs to that other scheduling group, and those are the priorities, some of the I/O scheduler. What the controller will do is it will change those priorities. We actually call them shares, but it's the same concept. And it will dynamically and automatically change those things, those numbers, to be lower or higher, and the CPU scheduler will uphold the proportion of the shares that each of them have.